I'm Jordan Cahill and I'm explaining part A. So this is L4. Perpendicular to it is the muscle force. L4 is at a 30-degree angle from the horizontal. So here, first we have to find the muscle force. So we take the body weight, which is the force of gravity, which is 300 newtons, and it's 0.1 meters away from the axis. And we have the weight of the potted plant, which is 50 newtons, also 0.1 meter away. So from that, we find 35 Newton meters, which is also the external torque. And with that, we solve for the muscle force, and we get 700 newtons. So then we have to resolve the body weight and the weight of the potted plant into its y components. So we have our triangle here for both. And for the weight of the potted plant, we do cosine of 30 with y over the weight of the potted plant. We find 43 newtons. And then for body weight, we do the same exact calculation with y over 300 newtons, and we find 260 newtons. And the compression force is the muscle force plus the y component of the body weight and the y component of the potted plant, and we get 1,003 newtons.
My name is Carly Levart. I'm doing problem B. So this diagram here, so this line is the L4 vertebra, and then I drew coming perpendicular is our muscle force. This is our axis of rotation. So this distance is 0.05 meters. And then further in, I had the body weight coming down and our plant weight coming down. So I resolved these forces. This is Y1, Y2. Oh, sorry, this is also at a 30-degree angle. And then I resolved this one to MFY, which is on the same line of MF, and we have our X component. So the first thing we did was solve for our muscle force. So I set internal torque to external torque, and then I got 300 newtons times 0.2 meters plus 50 newtons times 0.2 meters, so 60 plus 10 is 70, then divided by 0.05, and we got our muscle force of 1,400 newtons. And then we had to find the overall compression force on L4. So that is including our muscle force plus Y1 and Y2. So Y1 was found by taking the body weight times cosine of 30, which is this angle, and we got 250 newtons. And then for Y2, we did the same thing, just 50 times cosine of 30, which is 43.3 newtons. We added those two compressive forces to our muscle force for a total of 1,702 newtons.
Hi, I'm Alex Brownell, and I did problem C. Well, okay, it was problem D in the sheet, but we're gonna call it problem C. So I looked at the L4 and how that affects with a squatted position. So here you see that we have a 60-degree angle from the horizontal, and this is your L4 line. Here's your muscle force. So with that, we first needed to find our muscle force. So we set our internal torque equal to our external torque. So our internal torque was from the muscle force, and our external torque was from the body weight and the weight of the plant. So we multiplied that by the moment arm of 0.1 meters, and the body weight and the plant are at the same point. So we ended up getting a muscle force of 700 newtons. And then to find our compressive force, we know that we're going to take all of the 700 newtons from the muscle force because it's in line with that vertebrae, and then we took our body weight and our weight of our plant, and we broke them into X and Y components. So with that, we solve for X1 and X2. So we know that if this angle right here is 60 degrees and the horizontal and the vertical line of the gravity makes a 90-degree angle, then we know that our other angle is going to be 30 degrees. So if you like take this segment and put it right here, then you're gonna have 60 and then 30 degrees. So I did sine of 30 times the weight of the plant, and then sine of 30 times the body weight. And I added those to the 700 newtons to get a compressive force of 875.
Hi, my name is Jeffrey Yu, and this is part D. So basically in this problem, the subject is holding the plant at a 60-degree angle. So our back extensor muscle force is right here, and the body weight in the plant, because they're the same distance, 0.2 meters away, you can add up the vectors together and calculate it together as just one unit. So in order to get the muscle force, we set up our equation over here. We did external torque equals internal torque, and then we kind of just plugged in. And because our muscle force runs with the m of y vector, we know it's the same force, so it's 1400 newtons. And then in order to find, so that's our compression force on this side, and then for external torque, and then for this side, we just basically found the angles, and we plugged in once again, and we did cosine of 60 times 350, because that's the combined force of the plant and the body weight, and then we calculated just the y vector part, and then we added it up, and that was our compression force. Okay. So once you have all the numbers lined up, it's pretty easy to tell which forces are the lowest, which one's the highest. So C was our highest, lowest, A was our second lowest, and then all the way up to 1702. And then we basically subtracted the highest and the lowest compression force, and that gave us 875 newtons.